In this additional screencast for studying, you do not have to watch this one. This is a request from one of the students. Most of the equations are already written, and so I'll be using the laser pointer to point through them just to speed things up a little. So it might be a little harder to follow. Of course, you can always stop and replay it. Again, not required, but for those who are interested. So up until we got to our section on waves, we were basically motivating Maxwell's equations, building them up one at a time, starting with Coulomb's law, Gauss's law, basically, and then going to Faraday's law. So this is the more complicated form if we have inside material of basically Gauss's law right here. And then this is Faraday's law. This just came with magnetostatics and dynamics as well. And this part right here, up until this point right here, is Ampere's law, and then this is Maxwell's correction. So what you see here is in all its gory detail, Maxwell's equations. In the case that we are inside a substance, this is not a vacuum where there might be free charges, free currents, and the stuff, it also could polarize, and it also could magnetize. And usually we don't have all those cases happening at once. So let's go one case at a time, and the easiest one would be in a vacuum. There's a lot on the page right now, so if you just concentrate up here, these are those same equations on the other screen, but where there's no free charge, there's no magnetism, so H is gone. There's also no polarization, so P is gone. You'll notice there's some P's that are gone, and there's no free current, so that little current part on Ampere's law is gone. If I substitute this Maxwell's equation into this one, actually I do a little more math. I take del cross E, and then I substitute del cross B into here, what I arrive at as the wave equation for waves in a vacuum. All right, and so when you ever see two spatial derivatives equal to two time derivatives, you have a wave equation. And this occurs everywhere in physics. I don't think I have to tell you all the places it occurs. And here is just probably the most simple solution. This is a plane wave solution. We've dropped the real part. The complex form is much easier to use mathematically. But if you want to think about this is take the real part of this, and I'm just dropping the real because I'm lazy and everybody does that. This is really just the cosine of kz minus omega t that has an amplitude E naught and a polarization in the x direction. So it's traveling in z. We know this because k dot r, if k dot r is equal to kz, that means the k vector must be in the z direction. Okay, and then it's polarized along x. This is just one solution to the wave equation. The wave equation is basically, the solutions to the wave equation are any combination of sines and cosines, so I can keep adding these terms with different k's and different omegas, and those will also be solutions to the wave equation as well. So let's just start with an easy solution so we can motivate what's happening. If I plug this solution into this equation, I've done it this time, I won't do it on the subsequent equations. What I get is a k squared term out here. If I take two space, this is two space derivatives. All right, and then this is two time derivatives of that solution. And this one works just as we thought it would, so long as k squared is equal to mu naught E naught omega squared. All right, so as long as this k is related to omega by this factor, then this is a fair solution. Let's look at that a little bit. So another way of writing that is k squared is equal to omega squared over c squared, or k equals omega c, and this is our definition of the speed of light. And Maxwell didn't know, he had stumbled onto it. This constant E naught mu naught, 1 over the root E naught mu naught, is in fact the speed of light, c. Okay, so here's what this solution looks like. This is in a vacuum. There's nothing to damp the wave. There's nothing to, no absorption going on. And so remember, when we're tracing out sine waves here, it's really just the amplitude of the electric field vector. This is a vector wave. This is a vector E field that's changing. Its velocity is just c in this case in a vacuum. Again, we talked a little bit on the other screen that the k in this case, because of the solution I wrote, k is going in the z direction, the polarization is in the x direction, and k is just 2 pi over lambda. So everything is its vacuum value. Let's move on. Okay, this is more complicated. So now I'm going to say that free charges are 0. Free currents, that current term is gone, it's missing here. And this is just what I had before, but written in terms of chi. Chi is the electric susceptibility. Okay, so once again, if I go del cross E, So I would do a del cross E. That would be equal to a del cross minus dB dt, and then I substitute it in. This is just one mathematical way of substituting one of Maxwell's equations into the other. I once again get a wave equation. And if you look, it seems to be a subtle difference here, where this is E instead of E naught. But there's a lot going on that we need to talk about. So 2 space, 2 times, so we should have a solution that looks like traveling waves. This is the simplest part. This is a cosine. These amplitudes can actually be all kinds of different things. This amplitude here can be a function of space and time as well. But it always has to have this e to the minus kz minus omega t part. What's interesting in this, we're in a material. If you imagine the material now is stretching, the charges on it are stretching away from the nuclei, away from the molecule centers, and then compressing and then stretching the other direction. So we have some extra field going on. We have this polarization part that we need to take into account. This is just from your book. The permittivity, E, the electrical permittivity, is related to chi. And what the heck is chi? Well, it's just this factor by which the molecules stretch. All right, so there's more going on with K. We're going to look at this K in a little more depth. All right, so once again, we have the solution. Big page, so let's use the laser pointer to go one at a time. Again, that wave equation on the other screen, that solution rather, works if K squared equals mu naught, now not E naught, but E omega squared. So it seems simple, right? Everything's the same, but there's a little more going on, and we talked about this in class. E is complex because chi is complex. Chi is complex because the polarization, when you want the molecule, we're inside like a piece of glass or plastic now, and when we're trying to drive these molecules, well, they're neutral to begin with, and then their charges separate, and I stretch them one way and stretch them the other way, and they don't respond immediately. They don't respond. We can think of when light goes into glass, the molecules instantaneously absorb it, and how they shake is how they will re-emit it. Okay, so there's this instantaneous absorption emission, and so I need these things to shake to re-emit, but if they don't shake as strong as when the light went in, and if it doesn't shake immediately, I'm going to have some delay. So imagine you have a mass on a spring, and it doesn't go up and down immediately. That's where the index comes from, and guess what? Some of the energy is spent on this spring motion and doesn't get all re-emitted back out. All right, that would be absorption. So you're not expected to know why this is N and alpha C. This is just a way that what people, when they're talking about dielectrics, it's a nice way to solve it, and you'll see why. Okay, so the permittivity is complex because there is some absorption going on, and it's real. That was always part of it because there's some delay. The mass spring system doesn't respond instantaneously, and it doesn't allow all the energy back out. There's some damping going on. If I plug in my definition for N, so I can rewrite N as mu E over mu naught E naught. In our case, mu is really mu naught. We don't have any magnetism, so mu naught. For our case here, I'm leaving it general, but for our case in dielectrics, this is still mu naught. All right, but here's a way to write K now. K is just, it's a real part and an imaginary part. You can see taking the square root of this equation, this loses its square, this loses its square. I've pulled out an E naught. Basically what I've done is I've plugged in this for E and taking the square root to get this part down here. All right, and then here's what the index is. It's the ratio of the vacuum speed to the speed in the material. So now that K that we wrote on the solution wasn't quite right. We wrote it as K, and that's all right. But Griffiths likes to use the notation where the real part is K and the imaginary part is this kappa. All right, so K squiggle, that means it's a complex quantity. One way that we note that something's a complex quantity is K plus I kappa. And so if you want to look over on this side now, the real part of K squiggled is just K, which is omega over V or N omega over C. And then the imaginary part, which relates to the absorption, is the absorption coefficient alpha over 2. So if we stick this K back into our solution, we really should have a K squiggle, not just a K. What we find out is we have a part that's decaying. We have a part because of the alpha that's damping. And then we have a k here that's traveling at a different speed. So this is traveling at a different speed. I mean, that looks like, wait, why is that such a big deal? Well, it's not just omega c anymore. It's delayed by this factor of the index of refraction. Let's look at that in just a little more here. So here's what the solution looks like. It's a damped traveling wave. So because of the absorption of the material, because the spring doesn't want to transmit all its energy or goes back into the spring, it goes into the material. I have this damped wave. I still have the separation here is lambda, but guess what? Lambda is a little different. It's going to be typically larger. Depends what medium you're going into and from, but it's going to be 2 pi over the k of the medium. And the velocity is going to be the omega of the k of the medium. We brought this up in class. Omega, when you're going from vacuum or to a material or vice versa, omega always stays the same. The omega is determined by the driving field. However, the lambda and the v is determined by the medium itself. Okay, so omega is always the same, and then lambda and v are basically chosen by the medium in a sense how fast the molecules respond. And typically we don't do this for dielectrics, but I think it's okay. The 1 over e amplitude, so let's say this wave started up here, and when it gets to its 1 over e value, that would be the amount of z that you've gone is the depth into the material called the skin depth. So the 1 over e depth is 1 over k. The way we've written it, it's 2 over alpha, and that would be the skin depth. And so that's how far the wave made it before it decayed to 1 over its e value. Why 1 over e? It's just what we chose as the figure of merit. But guess what? That's a pretty good amount of attenuation. And so you know that if something is already down to its 1 over e value, it's pretty much gone. So skin depth is a measure of basically, wow, my wave's almost gone because it got burned up in my material and made this mass on a spring shake really hard, and the energy went into the spring oscillation instead of the re-emission of my wave. So just to beat a dead horse, why was this different than the vacuum? And it is fairly subtle because with the notation you can make it, you're just changing E naughts for E, but there's a lot more going on. Basically we had some polarization. The field was stretching molecules. And the stretch of those molecules, or how much they stretch, can be defined by the polarization P, or rather chi, which is also contained in this permittivity. So this permittivity E rather than E naught, or epsilon I should say, rather than epsilon naught, tells us that my wave is getting held by the material, and the material is going to re-emit it, and how much comes out will depend on the real parts and the imaginary parts of this. Or sorry, how much comes out depends on the imaginary part, and how fast it comes out, how quickly the material responds, depends on the real part of this. So it's a little sneaky because there is some stuff to polarize, which is contributing to the overall field, which in a sense you could say is the overall field now. I'm shaking these molecules, these neutral molecules up and down, and they're re-emitting my radiation. If they're delayed, then the speed of the wave is going to change. If the shaking is delayed, then the speed of the wave through the medium is going to change. If they burn up energy, then I don't get all my wave out. All right. So again, this is just the idea here is we have some driving field. We didn't talk about who created it. Somehow, whether it's sunlight, fluorescent light, something, somebody created this, and it's making my glass go up and down. And so we started solving equations already inside here where we knew the driving field. All right, basically once we have conductors, we have a pretty complete story. There's one more thing, though, to talk about, which only comes up when you're talking about more than one waves at a time. It's listed in Griffiths, and we might as well talk about it now because it comes up in quantum, it comes up in solid state, it comes up anywhere you have waves, and that's dispersion. We might have a solution. We might have a solution that is not just one sine wave, one cosine, but many, many cosines, right? We said the simplest solution you can have to the wave equation is one cosine. All right, so the more complicated solutions that I might have is a sum of cosines. And that sum of cosines, you'll just have to believe me in this picture. It's not quite true if we actually really add up my picture, but if I have the right strengths and the right frequencies, I can add up a handful of waves and they will make a wave packet. Any wave packet, whether it's a quantum wave packet or an optical pulse or an acoustic pulse or whatever, is the sum of many, many sine waves. And you can think of what's going on is you have constructive interference where some of the wave exists, and nice destructive interference out here That's how you make a wave packet. It's the only way you can make a wave packet. A wave packet must have many frequencies, otherwise it's not a wave packet. So what it looks like to us is it looks like there's only one sine wave here, but that's actually the center frequency of this wave packet. Remember, there's many other frequencies going on here. And the group of this packet, which is the sum, travels at a speed called the group velocity. So if I look at this spot here over time, as this packet moves, and if I can put a little marker on here and I can track how this packet is moving, that will be at the group velocity. The wiggly stuff underneath, which is the center frequency, it travels at a different frequency, or it could travel at a different frequency. So what you can imagine is this whole packet is traveling, and the wiggles are maybe slipping ahead, or slipping or kind of going behind because the group velocity is faster than the phase velocity. All right, and it can be at times that the phase velocity can actually be faster than the speed of light. So information travels at the group velocity. There is no way you would know this. This phase velocity, in a sense, is kind of this fictitious thing. If you only have one wave, then the phase velocity is the group velocity. And this is why group velocity is a difficult thing to talk about at the undergraduate level, because we're often not talking about wave packets. When we're talking about wave packets, again, the group of the waves travels at the group velocity, but the wiggles underneath, which is kind of like this average frequency, it might travel at its own frequency, and that's the phase velocity. The phase is what we defined earlier because we only had one frequency, and that's omega over k. If we had many frequencies, it would make sense to talk about the group velocity. In conductors, let's go back. We're assuming we have no magnetism. And if you're looking carefully, there's actually some polarization built in here, but really these can be thought of as mu naught, E naught. The vacuum values don't change that much from conductor to conductor. If they do, you do need to take this into account. But this wouldn't be from polarization anymore because there's no charge, there's no bound charge. There's all free charge in conductors. So these are equations, no magnetism and no polarization. And at the beginning, this one actually can throw a loop into our solving the equations, but it turns out that if there is free charge density inside the conductor, it always wants to go to the surface. That's one of our conductor rules. So it goes to the surface, it goes really fast. If you looked at the characteristic time scales, very fast, on the order of 10 to the minus, that's like 0.1 attoseconds. In reality, it's slower than this, but it's still fast. More like nanoseconds, but typically too fast that we don't really have to worry about it. And that's if there's free charge in there, and then once it goes to the surface, it's going to stay there. So our equation up here is modified to a simpler form. So then all of our equations are more simply here. This is our free current. We do have free current now because charges can move. And this was always here. That was Maxwell's correction. So if we, again, del cross E, and then we put this equation into the del cross E, we'll get a wave equation that looks like this, and it has this one derivative term. That's going to cause damping there. It's going to cause absorption. So we don't have a totally free traveling wave, but a damped traveling wave. And so this one's damped for other reasons, and it's because there's actually conductivity present. And the conductivity, it's not infinite, and or rather, there's friction moving these charges through the metal. So the equation, we can do solutions like this, but we know we have some foresight. We're going to make that k squiggle. We know it's going to be complex, or let's propose it's complex. That's the only way it's going to solve this equation. So if we follow the format in Griffiths, and these are pages 413, 414, we can write a complex k like this, such that the real part of k and the imaginary part of k, k squiggle that is, are these values here. And these look messy, and these are nasty, and that's why your homework assignment was, what happens when sigma is really big? Well, when sigma is really big, you can ignore the 1. Okay, and this thing just becomes the root of this thing squared. And in fact, you might even ignore the 1 here if it's really big. If sigma is small, you can binomial approximate and get rid of this root. Same thing down here. And so basically when sigma is really big or really small, we we can make these things look a lot simpler. If you notice when sigma is really small, that would be an insulator, this term goes away, and we're right back to where we were with dielectrics. And then dielectrics, the only reason, so imagine this, imagine sigma is 0, right? We get rid of this term, and then we're right back where the dielectrics. But what made the dielectric complex was this. This E had a imaginary part in it as well. All right, so if you cover up this part, we're right where we were for dielectrics, except now E, we allow in dielectrics to be complex because we have this mass of the spring model, and we know there's going to be absorption. We do the solution of the driving mass spring, and we find out it's a complex solution. All right, so conductors, there's a different reason. It's just because of this extra term in the wave equation, and this extra term is effectively giving drag as well for different reasons. Griffiths defines D as the skin depth, again 1 over K, it's the 1 over E amplitude. V again is omega over K, and lambda is 2 pi over K, but these are the K now inside the metal itself. So this is inside some kind of metal you can think of. Alright, and once again we know what the solution looks like. This is going to be a damped traveling wave. This solution, we get a decaying wave if there's an imaginary part. And this is repeat from the page before. The 1 over E attenuation is 1 over K. So it turns out our solutions for conductors and dielectrics are very similar, but for very different reasons. In the case of the conductor, you can imagine we have these free charges. We have a driving wave. And they can be driven through the metal up, down, up, down. There's no restoring force there, and it takes some energy to move them up and move them down. And so I lose energy from this wave. And again, if we think of this instantaneous absorption re-emission, as these things wiggle up and as these things kind of absorb the wave instantaneously, go up and down, they don't let out all the wave because we lose some energy to the metal itself. In fact, there's cases where you don't lose that much. We didn't talk about this. We could look at the model closer of these things going up and down and talk about friction and drag, and we can find out there's actually a case, the conductivity itself, the conductivity sigma is complex. We'd have to go back and do that. And you can find out in the case when there's some friction, sigma just equals sigma like we have it on the page before. Alright, so on the page before we have sigma, we don't allow sigma to be complex. We could, and that's actually more of a detailed story, but in cases where there is some friction of these charges moving up and down, guess what? Sigma is all real. In the case when there's little friction, sigma is imaginary. And then it's like you don't have dampening, and this would be the case of a plasma. So there's times we talk about the plasma frequency. But let's just leave it at our simple model in Griffiths. The reason why we had a complex K, complex wave vector in dielectrics was because of this model over here, this mass of the spring. And again, if we think of the absorption re-emission, these drive up and down, but they drive up and down not with the same amplitude, the same energy. Some energy is burned up inside this mass spring. On the mass spring model, we didn't talk about this. We talked about in class when all the energy goes into the massive spring system. It all goes in, then you get nothing out, or very, very little out. And that would be when you're on resonance. So in the case of light going through glass, we're not in resonance. We get everything through. In the case with light on metals, we're closer to an idea of a lot of drag, a lot of resonance, where these things are moving up and down and they burn up all their energy. There are cases though for metals where the metal looks transparent, and then there's cases like we talked about glass, things that burn up light would be if we're at higher frequencies, or sorry, higher wavelengths and lower frequencies, the glass atoms start shaking and then you don't get light through. So very far infrared waves will burn up in glass pretty easily. They won't go through a window. So this invisible light on the very red end won't go through a window. Visible light will. Very high frequency light will go through a window. For microwaves, right, it gets burned up. It doesn't go through water, which is transparent. So this K and this kappa, these are reasons why we can see through things. And as you want to get more realistic, then we have to take into account the fact that the conductivity, we didn't do this here, can also be complex. But for most cases, it's the real value of conductivity is decent enough.